Hello everyone, I am Rohini. I warmly welcome you to our presentation on the multi-core load balancing scheduler. In today's world, modern computers come equipped with multiple cores, but having multiple cores alone is not enough. The real challenge lies in using them efficiently. Imagine a restaurant with 5 chefs, but all other orders are sent to only one chef while others sit idle. This is exactly what happens in a poorly managed multiple core system. To achieve these goals, we have implemented a round robin scheduling algorithm combined with load balancing strategy. Round robin ensures that every process gets an equal share of CPU time through a defined time quantum. Load balancing gets an equal share of CPU time though a defined time quantum. Load balancing ensures that when a new process arrives, it is assigned the core with the least current load, making the distribution as fair and efficient as possible.
Thank you, Rohini. I'm Dipanjali, and now I will walk you through how the multi core load balancing scheduler actually works. So, let's start with the input. Here, the user provides three things: the burst time of all processes, that is, how long each process needs to run, and the number of CPU cores available, and the time quantum for round robin scheduling. Once the input is received, the system begins the load balancing phase. Each process is assigned to a core based on which core currently has the minimum accumulated load. This greedy approach ensures that no single core gets overwhelmed while others remain free. After assignment, each core gets its own independent round robin queue. In round robin, each process gets to run for a duration equal to the time quantum. If the process is not finished within that time, it is pushed back to the end of the queue and will get another turn later. This continues until all processes in that core's queue are completed. The output of the system includes a Gantt chart for each core, which visually shows the sequence of duration of process execution. It also includes a result table displaying the execution time for each core and utilization bar showing how heavily each core was used compared to the most loaded core. This visualization makes it easy to understand the efficiency of a scheduler at a glance. You can clearly see whether the load is well distributed or if some cores are handling significantly more work than others. Now I will pass on to Manish, who will explain the technology stack, system flow, and the conclusion.
On the right side, we can see the Gantt chart which shows how processes are executed step by step. Each block represents a time slice of execution for a process. Below that, we have the result table which shows total execution time for each core, CPU utilization percentage. This clearly demonstrates how workload is efficiently balanced across multiple CPU cores. Now I will demonstrate the working of our project. First we enter the bus time of process, for example 5, 3, 8 and 2. Next we enter the number of CPU cores, let's take 2 cores. Then we specify the time quantum, for example 2. Then we have to click the run scheduler. After running the scheduler, the system distributes process across cores using load balancing, ensuring that no core is overloaded.
Thank you, Dipanjali. I am Manish and I will cover the system flow, the technology used, and conclude our presentation. The overall flow of our system is straightforward and interactive. The user enters the burst time, number of core, and time quantum. The system then processes the data, first applying load balancing to assigned processes to cores, then running the round robin algorithm on each core independently. Finally, the result are displayed as a Gantt chart and summary table with utilization bar. The entire project was built using core web technology. HTML provides the structure of the interface. CSS, including glass morphism, styling animation, and gradient background, give the application a modern and visually appealing look. JavaScript handles all the scheduling logic, including the load balancing algorithm and the round robin simulation. In conclusion, our multi-core load balancing scheduler demonstrate how multiple CPU cores can be managed intelligently. It prevents any single core from being overloaded, reduce idle time across cores, and improve both throughout the responsiveness. The visual output, especially the Gantt chart utilization bar, make it easy for use to understand complex scheduling concept in an intuitive way. The project serves as a valuable educational tool for student learning operation system while also demonstrating real-world multi-core scheduling principles. In the future, we aim to add support from additional scheduling algorithms such as shortage of first and priority scheduling, include real-time animation for step-by-step process execution, and further improve the user interface. We sincerely thank our faculty and peers for their guidance and support throughout this project. Thank you for watching our presentation. We welcome Any question or feedback you may have. This conclude our presentation on the multi